Welcome back to my YouTube channel. I will continue with the properties of the Laplace transform, and I will revise now the differentiation property. This is what we will prove. The Laplace transform of the derivative of f with respect to time will be sfs minus the value f at 0 plus. It means when t is greater than 0. Fs is the Laplace transform of ft. The definition of the Laplace transform is given by the integral 0 infinity ft exponential minus st dt. By integration by parts, if I will put u equal to ft, dv equal to exponential minus st dt. So the integral u dv will be uv between 0 and infinity minus the integral from 0 to infinity of v du. So here I have du equal to df over dt times dt, and the v will be exponential minus st divided by minus s. So applying now the rule of integration by parts, so I have this term plus this term. I can put now 1 over s outside the integral because it is not dependent on time. And this value here, at infinity, the exponential is 0. And at 0, the exponential is 1 and ft is replaced by f of 0. So this is the Laplace of the Fourier, the Laplace of ft will be equal to 1 over s times f0 plus 1 over s integral derivative of f exponential minus st dt. Now, I will conclude that the Laplace transform of df over dt, which is this expression, so I will multiply this equation by s, I will get the following. So the signal may not be continuous at time t equal to 0. This is why we will replace Laplace of the derivative of f with respect to time to be sfs minus f at time 0, 0 plus. It means just after t equal to 0, 0 plus epsilon, okay? So the nth derivative of f, its Laplace transform can be written in this form. You see that we start from Snfs, where fs is the Laplace transform of ft. Then I will decrease the power of s by 1 in each step. Always I have minus, minus, minus until the end. So I will decrease the s, the power of s, which is here n, by 1. I will get minus s n minus 1, f of 0 plus. Then minus I will decrease by 1, and I will increase the order of differentiation by 1. So I will have f prime of 0 plus. And I will continue decreasing the power of s by 1, and increasing the order of differentiation until I will arrive into s power 0, differentiation n minus 1 at 0 plus. To prove these results, we can start from the previous results, which indicates that the Laplace transform of the derivative of f is sfs minus f at 0 plus. Now I can say that the Laplace of the second derivative of f with respect to time, it is s times the Laplace transform of the first derivative of f with respect to time minus f prime at 0 plus. Okay, so this is what I am writing here. So the Laplace of the second derivative of f, it is s times what? Times the Laplace transform of the derivative of f, which is this this expression, so I plug it here, minus f prime at 0 plus. So I can expand, I will have S2 Fs minus S f of 0 plus minus f prime at 0 plus. So this is a special case of this when n is equal to 2. If I will go now to the Laplace transform of the third derivative of f with respect to time, if I will use these results as a starting point, I will have the Laplace transform of the third derivative of f with respect to time to be s times the Laplace of the second derivative that I got it in this step, okay? Minus f double prime, it means the second derivative of f with respect to time evaluated at 0 plus. If we will expand this term, we will get s cube fs minus s2 f of 0 plus minus s f prime 0 plus minus f double prime 0 plus, which is also a special case of this formula when n is equal to 3. Let us show the application of the differentiation property of the Laplace for solving differential equations related to circuit analysis. So this is an RL circuit. At time t equal to 0, the switch is closed at time t equal to 0. When time is negative, it means there is no circulation of current. So the current will be equal to 0 when time is negative. So this is a good illustration of the Laplace, because the Laplace always start from 0 to plus infinity. It means we are dealing with signals where the time is varying from 0 to plus infinity. It's like we are in a situation where the switch is open, so we don't have any signal at that when time is negative. At time t equal to 0, we close the switch, and the process starts from that instant. So this circuit is described by a first-order differential equation with respect to the current. So if we write the Kirchhoff voltage law, we write minus V plus Ri plus L di dt equal to 0. So the V here, it is V times ut, okay? So it is the V times, so it is a constant. It is a constant multiplied by the step function, okay? Now this is a differential equation in time. So I would like now to compose the Laplace transform for both sides of this differential equation. So here I will have L. So the Laplace of di over dt will be s is minus the current I at 0 plus, which is exactly the differentiation property that we have proved in the previous slides, plus Ri equal to V, and the Laplace of ut, the step is 1 over s. You see now, when we compose the Laplace transform in both sides of this differential equation, we get something which is independent from time, okay? So here is like we are solving a normal equation with respect to the variable is. So now if I will extract is from this equation, I will get is equal to this. So this is a rational function in S. If I will decompose this rational function into two terms, which is A divided by S plus B divided by S plus R divided by L, I will get in one side, if I will compose now the inverse Laplace transform, I will get A to be V divided by R. Okay. So this is the step, and I have A equal to V divided by R. Okay. And the Laplace of 1 over S plus R divided by L, it is the exponential of minus r over lt times ut, of course. Okay, so the b here, it is minus v over r. Okay, so now we have been successful in writing the solution of this differential equation by going to the frequency domain. How can we go from continuous time to frequency domain? We compose the Laplace transform in both sides of this differential equation. We solve in the frequency domain, and we get the solution Is as a complex function. And then we will compose the inverse Laplace transform in order to get the expression of the current IT for all time positive. Here I am giving some useful decomposition rules that helps you in calculating the inverse Laplace transform when you have a general transfer function fs, which is gs divided by the product of terms of the form s plus bi, I between 1 and n. In order to have this decomposition, the bi should be different. It means b1 should be different from b2, from b3 until bn. So if you have a polynomial function here, which has different roots, in this case, this decomposition of that form is possible, and I can get the coefficient alpha I from this rule, which is alpha I, it is the function multiplied by this factor s plus bi, okay, evaluated at the root of each term, okay, which is s equal to minus bi, the I between 1 and n. For example, if I would like to calculate alpha 1, I will multiply fs by s plus b1, and I will evaluate this product at s equal to minus b1. If I want to get alpha 2, I will multiply fs by s plus b2, and I will evaluate the product at s equal to minus b2. I will continue this process until I will arrive to the last term, which is s plus bn times fs evaluated at s equal to minus bn. In other situation, we don't have roots different. We may have some roots. It means the denominator of this transfer function may have a root of multiplicity equal to r. So here we see that s equal to minus b is repeated r times. How this function can be decomposed into simple rational function. So we can decompose it in that form, and we see that s plus b is repeated by with power different from the first to the last, and these coefficients from alpha 1 to alpha r are determined from this differentiation formula. So I will call q the transfer function multiplied by s plus b power r, okay, and then I will differentiate it to get the different coefficients from alpha 1 to alpha r, okay. Now we may have roots of multiplicity greater than 1 multiplied by some product where I have different roots, okay. So we can compose, we can have a decomposition like this plus another decomposition plus this, okay. We will see, we will practice this kind of decomposition in my next videos. Now I will study the property of Laplace when I will multiply the function ft by time. So I will start from the fact that fs is the Laplace transform of ft, and then I will differentiate df over ds, and I will multiply it by sign minus. So it will be minus d over ds times now d over ds of the Laplace of ft, which is this. Now, if I will enter the differentiation inside the integral, I will differentiate with respect to s, so I will get the t here. And this is nothing but the Laplace transform of t ft. It means the Laplace of t ft, it is equal to minus d over ds fs, where fs is the Laplace transform of ft. In the general case, if I am multiplying the function f by a polynomial function of time t power n, I will get minus 1 power n differentiation power n of f over ds. How can we get this nth order rule starting from this? Okay, we can easily prove it by starting from this one, because we have proved this one. Now, if I will replace, if I will replace tft to be the new f, and I will put here t, it means it's like I have t square ft, or here, okay? So if I will plot, if I will take the case where n is equal to 2, I will have t square ft. That I can write it as t times tft. But tft, it has a Laplace equal to minus df over ds. So if I will apply minus of the derivative of minus of df over ds, I will get the second derivative of f with respect to ds2. Okay, and this will be a special case of this nth order formula when n is equal to 2. Okay, so if I will continue with the 3, if I will prove for 1 and then 2 and 3 and 4, I can see the sequence, and I can make a generalization of the Laplace transform of t power n ft, which gives minus 1 power n differentiation n of fs by ds. The initial value theorem. What is this initial value theorem? It means that I am in the frequency domain, and I would like to know what is the value of the function in time at time t equal to 0. So generally, when I am in the frequency domain, I don't have any knowledge what is happening in time. But this initial value theorem gives us an insight. It gives us an information about the function in time at time t equal to 0 when I am already in the frequency domain. Now, we have proved that the Laplace transform of the derivative of f with respect to time, it is fs minus f at 0 plus. Okay. Now, I will compose the limit when s goes to plus infinity. So the limit of this integral when s goes to plus infinity will be equal to what? To this limit when s goes to plus infinity. When s goes to plus infinity, since the s is composed from a real part and imaginary part, and the real part is assumed to be positive, it means this term will be 0 when I will tend s to plus infinity. Okay? It means limit of this function between bracket will be equal to 0, which means that the value at time 0 plus, it is the limit of SFS when S goes to plus infinity. And this is the beauty of this theorem is here. It means I am in the frequency domain and I am able to know what is happening to my signal in time at time t equal to 0 without composing the inverse Laplace transform. It means generally when we have Fs, we compose the inverse Laplace transform in order to get Ft and then evaluate Ft at time t equal to 0. But here we don't need to this. We have just to compose a limit of SFS when S goes to plus infinity will be the value of the function at time t equal to 0.